questions?
Can you go over the last one on the master set?
Chapter 27.
Yeah. You kind of have to do this problem, Jeff, because there's like a lot of information in that problem. And it says like one thing happened, and then another thing happened, and then.
Oh, that's the capacitor one.
Yeah.
It's just manipulation of formula.
Well, that's great.
So we start out with a parallel plate. I gave you the area, I think.
Yeah, 900 centimeters square.
So it's 30, I think I even said square.
Yeah, square, gap between the plates is 0.5 centimeters.
So under 10% of the 30,
So, good enough for the
infinite plate approximation. It was hooked to a battery.
12-volt battery, constant, dielectric constant, 1.5.
It starts out with nothing in it, then we stick in the dielectric constant of kappa 1.5,
Yes.
Yes,
and then the distance becomes
triple.
3 times whatever the initial distance is. And then unhook the battery.
Yeah. I know, I'm pretty sure the electric field is going to stay the same.
Well, there's 2 different electric fields.
Right, I meant the overall, or the total electric field.
All right, the equations that we're working with here is, I know capacitance is equal to kappa epsilon naught A over D for parallel plate capacitor. Also equal to Q over delta V for capacitors in general. So this is specifically parallel plate, parallel plate capacitor, and this is general. I know that the electric field from the plates is equal to sigma over epsilon sub naught, which is Q over A epsilon sub naught. And then E total is going to be sigma over epsilon, or sigma over kappa epsilon sub naught. And it's also delta V over D. So that's what we're working with. The unhooking the battery, generally if you unhook the battery, or disconnect, probably the better word. If you disconnect the battery, you're now setting the charge. The charge is now fixed. If the battery is hooked up, then the voltage is fixed. However, if the last thing you do is to disconnect the battery, then it really has no effect. It would only have any noticeable effect is if you manipulated the capacitor after disconnecting or connecting the battery. Actually, disconnecting. If you connect the battery, that could change things immediately.
So the voltage will stay the same?
So the voltage will stay the same.
Because it was 12 to begin, 12 to begin with?
Yep.
And it's 12 after you disconnect it, because it stores that charge.
Yeah.
The difference is, Q.
So, yeah, voltage is going to stay constant, so Q is the thing that's going to change. As you manipulate it, you are increasing the dielectric constant by 1.5. The distance is increasing by 3, so the net result is your capacitance is being cut in half. The voltage is constant, the charge is affected. If the charge is affected, well, if there's less charge, then the plates get, the electric field on the plates change.
But not the total.
The total, let's see, well, Q got cut in half. Area is the same, epsilon's not the same, so the electric field gets cut in half. from the plates, or, sorry, probably sigma gets cut in half. Kappa is 1.5 times the initial value, so the total electric field gets smaller also, so that's cut in half, and then we got a 1.5 down here, so basically, the total electric field is the third of what it originally was.
Third.
Cause I got a 1/2 and then a 1.5 here, V2 times 1.5.
Oh, 1/2, 2 times, yeah, okay.
Or voltage stays the same, the distance is triple.
The electric field, are you on electric field strength between the plates, from the plates?
That's this up here.
Alright,
And then the difference between these two is because the dielectric creates an electric field up in the opposite direction. So it drops the total electric field.
so the electric field between the plates stays the same?
No, the electric field,
Between the plates, from the plates?
because Q gets smaller.
Alright, you guys get smaller.
Area stays the same, epsilon's a naught is epsilon's a naught.
You know how much it gets smaller, or is it just like, we just know it gets smaller by some amount because?
Well, it's gonna be by half above, it's gonna be half the original, because if we do, original capacitance, kappa, epsilon sub naught, well, original capacitance, epsilon sub naught A over D sub naught, whatever that is. And then the new capacitance is going to be 1.5 epsilon sub naught A over 3 D sub naught, which is epsilon sub naught A over 2 D sub naught. So it's half the original capacitance, which the 1/2 C sub naught is equal to Q over delta V. That stays the same, so Q has to be half the original charge, which means that this is cut in half.
So your, electric potential of the negative charge plate?
But
The last one was the electric potential of the negatively charged plate.
the electric field,
Electric potential, yeah.
that's potential difference.
Yeah.
We can't know, all we know is what the difference is between the two. We really can't know what voltage is at any particular point. So when you have a 12-volt battery, all you know is the difference in the potential between the positive and negative leads is 12. You have no idea what the potential is at any particular point.
That's what you're saying is a third, because the distance increased by 3, so it's 3D, so it's 1/3 of the, potential then?
Right. Which matches what we got when the charge density was cut in half, the denominator was increased by 1.5. We'll get the same answer. And if we didn't, then something went wrong. I think there was some spoilers in there, sorry about that. Other questions, or?
Could you draw up 5? It's a, draw it a series or a circuit.
Actually, it'd be more helpful if you explain how you got 5, because I just was like trial and error on it, like over and over.
Yeah, I still don't know if I drew it right.
There is a certain aspect to trial and error on it, but you,
I mean, the only thing I could infer to begin with was that it was going to be a combination of parallel and series.
Yeah.
But that's all I could really get, and I was just like plugging in numbers until it worked, you know? Like,
well, if you add in parallel, you're going to increase the capacitance. If you add in series, you're going to decrease the capacitance. So, using that as a starting point, so if you started with 25 and you want to decrease it, well, something's got to go in series with that.
and then you put it in series, figure out what that is. Well, you need to go up, well, then let's add something in parallel. You need to go down, add something in series. But that's the essence of the approach. As far as drawing it goes, well, that's the one thing that's the biggest mistake students make, besides miscalculating, is forgetting to show where the leads are. Because if I, in theory, did this as a, so I have 4 capacitors here, I'm definitely getting a different result if I put the leads here, or here, or here, or here, or here, or there. Potentially I can get 6 different capacitances out of that setup, depending upon where I put the leads. So just make sure I know. And generally you indicate where the leads go by something like that. If I took a capacitance meter and was trying to actually measure the actual capacitance.
I just put them as like going out into 2 wires that connected to the circuit. And like,
Okay. I
feeling
mean,
like
some people
you're-
throw in a battery too. Which I, not necessarily what you just said, but
Yeah.
if you did that, I know where the leads are.
Yeah.
For capacitors in parallel and capacitors in series, what are the equations? Is it C1, C2, C3 for parallel, or is it that for series?
The C1 plus C2 plus C3,
Yeah.
that is capacitors in parallel.
In parallel, and then in series it's 1 over
Yes.
C1. Okay.
And it's opposite for resistors.
Yes. Trying to read your look there, Nate. Is that the look of,
Yeah.
I messed the whole thing up, or?
No, I did it right.
Okay.
I'm just confirming and like trying to find a way to remember it in my head. Is there like?
Intuitively, resistors make more sense to me, and I know capacitors is the opposite. So,
Oh.
that's how I do it, but,
Yeah.
you know,
Okay.
some say that each person's mind is different than everyone else's.
Yeah. Okay.
Dr. Foss, can you go over, question 4, part B? I just didn't know how to go about it.
All right, so I gave you the electric potential. Find another point that shares an equipotential line with 1, 2, 3. All right, so you said 4B?
Yes.
Okay. So if you plug in, so 1, 2, and 3 are X, Y, and Z, so ordered pair. So if I just plug 1, 2, and 3 into that equation, I can find the electric potential at that equation, at that location.
Okay.
And so it's just a matter for part B of find another combination of numbers that will get you the same answer
Okay.
if you plug in.
So just any combination.
Yeah, just wait for anything that'll work.
Okay.
And some people will see an easy solution there, and some people will come up with something complex. Depends on how much you,
Which work you want to find.
yeah. And then, yeah, you just asked about B, so is that sufficient?
Yeah, that answers my question.
Okay. Other questions?
So how do you know where the leads go? So
If so let's say I've got a 5 on an H10, 15, and 20. In order to figure out what the equivalent capacitance is, I need to be able to figure out what's in series, what's in parallel. If I put the leads here and here, so I have this circuit set up, I take my capacitance meter, or take my multimeter, put it on capacitance,
take my two leads, if I put those connections there, those are in series, those are in series. So that will be 1/5 plus 1/10. 3/10. And so the equivalent capacitance here is 10/3. And I have 1/15 plus 1/20. So 60, so 3, 4, 7, 6, 7/60. So the equivalent capacitance here is 67ths. And then those are in parallel with each other, so 180 plus 70, so 250 21st farads. Assuming I didn't make the notes there. If instead, take the same setup, 5, 10, 15, and 20. I take my two leads and I stick it here and here. Well, if I do that, these are in series, those are in series. If these are in series, I have 1/10 plus 1/20, 3/20, and so this equivalent capacitance is 20/3. And this equivalent capacitance, I have 1/5 plus 1/15. That'll end up being 15/4. And so that is in parallel with this. And so my total would become 60 plus 80, so 140 twelfths. So that's why I need to see where the leads are to know how to figure out what's in series, what's in parallel.
Okay.
I've seen way too many times people just give me
Yeah.
that, and now I could guess what the intent is, but I want it to be more explicit. Look like you'll follow.
So on the side, is it always like on the side of the series, like this is parallel or it doesn't matter? Depends on.
If you think about current flow, at least the way I do it, I think about current flowing in one lead, and then it'll split. Any current flowing across here will also flow across there, so therefore, series. If those are in series because the same current would flow across them. There's no place for current to deviate. Anything flowing across that has to flow across this.
Oh, okay, okay, that makes sense.
That's series. Other questions? We last left off dealing with this equation.
Just start a new one so we can categorize better.